Morning, CCTI AP Calc. Mr. Pashar here. I hope this finds you well on Friday. I'm hoping the weather improves a little bit eventually. It's kind of depressing. Kind of tired of being in the house. There's nowhere to go. You know, just want to get out and do things already. You know, I want to plant my garden. You can't go to the store to buy seeds. It's not essential. Apparently, they want you to grow vegetables and you can't even buy the seeds. I don't know. But what I do know is I'm going to talk to you about the definite integral today and what we know. So we have this definition that you've seen in the text that says essentially if we take all of our sample points, so if we take the limit of the sum of all these sample points, which is nasty, we saw the easier part, which was just taking the left sample points and the right sample points, right, and getting an approximation. But then if we went another step forward like mathematicians did, we have the Riemann sum part, which is a little more difficult, so we skipped it for now. We just don't have the time, and based on the conditions too. If we go ahead and take the limit of all these sample points, that gets us to the definite integral, to make a long story short. So the next problem is, okay, good, we got this definite integral. That's going to be the area under a curve, the exact area, not an approximation. But then how do we evaluate things that look like that? We know how to do indefinite integrals, but how do we do definite integrals? So the first thing I'm going to show you is how do we go ahead and transform a limit that's written in this way. So say for example we have something that looks like this. The limit as n approaches infinity of the summation of I equals 1 to n of cosine x sub I delta x over the interval from 0 to 2 pi. It's very easy to rewrite this. Our lower bound of integration is 0, and our upper bound is 2 pi, and our function is cos x dx. So we get rid of the delta x. Delta x, remember, stands for the thickness of those approximating rectangles, right? The thickness and the subintervals will tell us. And now we can transform it. So this is a basic thing to do, just rewriting the limit in terms of the definite integral that it represents. And you'll see that in the text and perhaps on Khan Academy in your work. But the main focus today is this idea of this evaluation theorem. So mathematicians had to painstakingly go through this thing with the limit in order to find the exact area under the curve. But we need to have a method. We can't keep doing that forever. So the evaluation theorem, which is also known as FTC Part 2, Fundamental Theorem of Calculus Part 2, which, not to take anything away from it, is a huge accomplishment in the world of mathematics. Huge, right? Huge accomplishment for mankind. But this gives us, and again, mathematicians had a slave way for years doing this stuff. For example, there was a French mathematician in 1635. He found the exact area under sine and cosine, using this ugly idea of limits, which we're not going to do. But the evaluation theorem later, 1660s, 1670s, brought to you by Newton and Leibniz, should say the following, that if f of x is continuous over the closed interval from a to b, then what we know is if we want to integrate f of x from a to b, it's as simple as taking the antiderivatives and evaluating them at their endpoints. Can you believe that? All that crap with approximating rectangles boils down to the fact that if we could find the antiderivatives and evaluate them at the endpoints, that's how you solve your definite integral, right? So let's look at an easy example to start off with, the one that we began the section with the other day. The integral from 0 to 1 of x squared dx. So that was, if you remember, the area under the parabola from 0 to 1. We found an approximation using left-hand endpoints. We found an approximation using right-hand endpoints. You could find the midpoint of the subinterval, but now we want to find the exact area. And what it boils down to is this. Taking the antiderivative of x squared, which is x cubed over 3, and evaluating it at the endpoints, 1 and 0. So you have 1 cubed over 3 minus 0 cubed over 3, which is just 1/3. So look at that. Without doing any ugly limits and sigma notation, you have the exact area of 1/3. And that is how we find a definite integral. Now, are they all going to be this easy? Of course not. Some are going to take a lot of creativity, algebraically or trigonometrically, but for now we're just going to look at the basics on how this works. So let's look at another example. One that the French mathematician de Roberval looked at initially, which is this integral here, 0 to, I believe it's pi over 2. Yep. 0 to pi over 2 of cos x dx. So we want to integrate cosine from 0 to pi over 2. So graphically, what does that look like? Well, if you remember, cosine at 0 is up here at 1, and at pi over 2, it's at 0. So we're looking at part of its curve that looks like that. So we're looking for the area underneath that curve. So we're going to go ahead and find it. So take the antiderivative of cosine, which is sine. So we got sine of x, and we're going to evaluate it at pi over 2 and 0. So by fundamental theorem of calculus part 2, we could say that, okay, this is going to be sine of pi over 2 minus sine of 0. Sine of pi over 2 is 1, minus sine of 0 is 0, so the area is 1. So this area under the curve is represented by 1 unit. No nasty limit to compute, just good old fundamental theorem of calculus. So this one worked out nicely for us. They're not all going to work out nicely. Sometimes you're going to require substitution, which will, by the way, be the next video. How do we do substitution with a definite integral? Because there's a cheap way to do it, or a cheap way, right? I like the cheap way though, less errors. Or you can rearrange the whole integral to make it work. So we'll talk about that next time. Well, let's look at another example here. One that's a little more tedious. How about this integral here? From the integral from -1 to 6 of 3x to the 7 plus 4x cubed minus 2x dx. So we want to integrate this thing. But again, essentially we could find the antiderivative of each piece and integrate it at the endpoint. So 3x to the 7, if we integrate that, that's going to give you 3x to the 8th over 8 plus 4x cubed would be 4x to the 4 over 4 minus 2x would be 2x squared over 2, and it's evaluated at 6 and -1. All I'm going to do in the next step, guys, is simplify a little bit algebraically to make the computation just a little more better. So 3x to the 8 over 8 plus x to the 4th minus x squared evaluated at x equals 6 and x equals -1. So by the fundamental theorem of calculus, we can just plug in these endpoints. So just got to be careful. It's going to be 3 times 6 to the 8th over 8 plus 6 to the 4th minus 6 squared. I'm going to put the minus in between in brackets because we're subtracting. So you're going to have 3 times negative 1 to the 8th over 8 plus negative 1 to the 4th minus negative 1 squared. Again, just be careful with the minuses, and then we have some parentheses there. So there's a lot of computation here, but again, nothing that you can't handle. Let's take a look at what we got. What this is going to turn out to be is 631,116 minus 3/8, which as a decimal would be 631,115.625. That's what it would look like. So quite a big area, of course, in terms of units. So again, this is probably a good place to stop and pause to think about what we've done here. And I'll come back and we'll look at another example. And then we're going to look at a pitfall that often happens to us if we're not careful, okay? Okay, so let's look at another example where we have to be a little bit careful as well. How about the integral from 4 to 9 of the square root of x times x squared minus 2 dx? Now, as we learned with indefinite integrals, we went through a progression. So we were able to verbatim use definitions, but then we looked at, well, sometimes we have to do manipulations in a problem. And that's what has to be done here. We're going to have to distribute this root x through the parenthesis, and we can do that because it's not held up by an exponent up here. So before we integrate, let's do that. So if this is x to the 1/2, so x to the 1/2 times x squared. Add the exponents at x to the 2.5 or x to the 5.5 minus 2x to the 1/2 dx. So now we could go ahead and integrate. So this is going to be 5/2 plus 1, that'll be 7/2. So x to the 7/2 over 7/2 minus 2x to the 3/2 over 3/2 evaluated at 9 and 4. So that means we got 2/7 x to the 7/2 minus 2/3 times 2 x to the 3/2 evaluated at 9 and 4. Okay? So I'm going to come up here and I'm just going to write in what we have. I'm going to do a little more simplifying. So this will be minus 4/3 x to the 3/2 evaluated at 9 and 4. Okay? Hope you're following along. Just be careful, we got to plug in all these endpoints. So this is going to be 2/7 times 9 to the 7/2 minus 4/3 times 9 to the 3/2 minus, we're going to have 2/7 times 4 to the 7/2 minus 4/3 times 4 to the 3/2. So that's a lot. The tricky part really is just the the exponents because they're fractional, right? So you kind of run into a little bit of a problem. That's not a big problem. Now let me help you a little bit with the simplifying at this point here. 9 to the 7 halves. What does 9 to the 7 halves mean? That means you take the square root of 9, which is 3, and raise it to the 7th. So I'll write this as times 3 to the 7th. Minus 4/3 times 9 to the 3 halves. Well, square root of 9 is 3, and you cube it, so I'm just going to write that readily as 27. Minus, over here it says 2/7 times, you got 4 to the 7 halves, so that means you have the square root of 4, which is 2, and raise it to the 7, so that's 2 to the 7th, minus 4/3 times 4 to the 3 halves. Square root of 4 is 2, 2 cubed is 8, so I'm going to write that in readily as 8. Now when you go through this, just be careful, right, because you have that minus in between. What you have over here on the left is 4,374 over 7 minus 36 minus, over here you're going to have 256 over 7 minus 32 over 3. And again, I kept the grouping symbols there just so we don't have any sign issues. It'd be a shame to mess up after going through all the calc part to make a silly mistake. But usually 9 times out of 10, that's where the dumb mistake comes in, myself included. And when you sum this all up, you'll have 11,822 over 21. That would be the exact fractional answer. That would be the area under this ugly curve. Okay? So that's how you would apply the fundamental theorem of calculus. Again, a very useful tool. Who the hell would want to go ahead and try to do summation notation for this, right? So luckily we have this great theorem. This would probably be another good place to pause, see if you could do this problem. I'm going to come back with one more thing, and a very important thing. What happens when we abuse, right? You're thinking, how can we abuse a theorem? But it happens all the time. What happens if we abuse a theorem that we have here? So stay tuned. Okay, so let's take a look at an integral here. The integral from -1 to 1 of 1 over x squared dx. Okay, so let's go ahead and integrate this thing, right? So what do we know? Well, it says that we could take the antiderivative of this and evaluate it at the endpoints. So I'm going to rewrite this as -1 to 1 of x to the -2 dx, because this is a little bit easier to take care of. So now this is going to be x to the -1 over -1, evaluated at 1 and -1. So that means what we're going to have here, I'm going to rewrite this as -1 over x, evaluated at 1 and -1. So that means we have -1 over 1 minus -1 over -1, which would be -1. This becomes a plus, and -1, which would be -2. Okay. Now, here's the thing. Algebraically, that's sound, right? X to the -2 does have an antiderivative of -1 over x. We're not going to dispute that, right? Right? Nod your head, right? That's sound. But what we did here, my friends, is we abused FTC. So in all this work here, we abused FTC Part 2, and Leibniz and Newton would be rolling in their graves. Because we got kind of caught up in this nice little rule, and we forgot what the rule says. It says that F needs to be continuous. Needs to be continuous over that interval. So when we look at 1 over x squared over the interval from -1, there's a problem. The problem is 0. 0 is clearly in there, and you can't divide by 0. So f of x is not continuous on that interval from -1 to 1. And if it's not continuous, that means this integral does not exist. So that integral actually, guys, does not exist. Even though we were able to do the calc, it doesn't exist because we defied FTC Part 2. Now, we can, in fact, actually solve that, but that's a Calculus 2 type problem. That gets us into the realm of what we call an improper integral. And we talk about the idea of divergent and convergent integrals and getting answers like -infinity and infinity. But for now, this thing does not exist. So you got to check out your bounds. The moral of the story, check out your bounds before you integrate and ask, does any of those bounds give that function f a problem? Because if it does, we can't integrate. This also brings us to another useful tidbit of information here. So suppose that nothing was abused here and this was continuous. There's actually another problem here we run into. The problem is that we end up getting a negative number, and a function like 1 over x squared, if we had a different interval, say for example, it was 0 to 1 or so, or -1 to 3. There's a rule that says if f of x is greater than or equal to 0 over the interval from a to b, that means the integral of that function has to also be greater than or equal to 0. In other words, if that function is greater than or equal to 0 for all x on that interval, then so does the integral itself. And that certainly would not be the case there with a function like 1 over x squared, right? Because if you clearly see, you plug in -1, it's going to give you 1. So this would be the second mistake. If you end up getting a negative number, this is impossible because the fact that that function, 1 over x squared greater than or equal to 0, when x is contained in -1 to 1. So that's the second thing you gotta look out for. So abuse of FTC Part 2, and then this fact here, if your function's greater than or equal to 0 over the interval, then your integral itself has to be greater than or equal to 0 over that interval, or you made some kind of computational mistake. So with that being said, this is a good place to stop. I hope this made sense to you. If not, please call, send an email. I'll gladly be able to go over it with you. You should be able to work on your assignment. Remember, that's due on Tuesday. It's about lunchtime, I guess. So I'm getting hungry. I don't know about you guys. I'm getting hungry. Looks like it's foggy outside. Depressing. What else? What else is new, right? We're all depressed. But in any case, I hope you're doing well. I hope you're understanding the calculus, and I'll see you guys next time.